Have you ever looked up at the night sky and wondered what lies beyond the stars? Our universe is vast, but even the most powerful telescopes can only see so far. What lies beyond that edge? Does something exist out there, or is it just an empty void? Join me as we explore the mysteries of the universe's boundaries, what might exist beyond the observable, and if beyond the observable even exists. Defining the observable universe. The term observable universe refers to the part of the universe that we can see and study. It includes all the stars, galaxies, planets, and other objects that are within our view. This view is limited by the distance light has traveled since the beginning of the universe, which scientists estimate to be about 13.8 billion years ago. Because light travels at a finite speed, we can only see objects whose light has had enough time to reach us since the universe began. Imagine standing on a hilltop with a flashlight. You can only see things that are within the range of your light. Similarly, the observable universe is like our cosmic flashlight's range. Anything beyond this range is invisible to us, not because it doesn't exist, but because its light hasn't reached us yet. The size of the observable universe is enormous. It's estimated to be about 93 billion light-years in diameter. This means that the farthest objects we can see are 46.5 billion light-years away from us in every direction. The reason this number is bigger than the universe's age in light-years is because the universe has been expanding since the Big Bang, stretching the distances. The boundary of our observable universe is known as the cosmic horizon. This is the edge beyond which we cannot see, no matter how powerful our telescopes become. This horizon is set by the speed of light and the age of the universe. Light travels at a speed of about 300,000 kilometers per second, 186,000 miles per second. Since the universe is 13.8 billion years old, the farthest light we can see has been traveling for 13.8 billion years. However, because the universe is expanding, the objects that emitted this light are now much farther away than 13.8 billion light-years. Our understanding of space has come a long way over time. Ancient civilizations looked up at the sky and saw stars and planets, but they had no idea how far away these objects were. They often believed the stars were fixed points on a celestial sphere surrounding the Earth. Historical perspectives on the universe. Ancient civilizations all over the world developed their own ideas about the universe. These early models, called cosmologies, reflected the knowledge and beliefs of their times. For example, the ancient Egyptians saw the sky as a goddess named Nut, arching over the earth, which was her husband Geb. The stars were thought to be jewels on Nut's body. The Egyptians believed that the sun god Ra sailed across the sky during the day and journeyed through the underworld at night, bringing light and life to the world. In Mesopotamia, the Sumerians and Babylonians envisioned the universe as a flat disk floating in water. They believed the sky was a dome with stars embedded in it, and that it separated the heavens from the earth. The Babylonians were skilled astronomers and made detailed observations of the movements of stars and planets. They used this knowledge for practical purposes, such as creating calendars and predicting eclipses. The ancient Greeks developed more complex models of the universe. One of the earliest Greek philosophers, Anaximander, proposed that the Earth was a cylinder floating in space. Later, Pythagoras and his followers suggested that the Earth was a sphere. This idea was supported by observations such as the shape of the Earth's shadow on the moon during a lunar eclipse. Plato, another Greek philosopher, believed that the heavens were perfect and unchanging, and that celestial bodies moved in perfect circles. His student Aristotle further developed these ideas, proposing a geocentric model of the universe. In Aristotle's model, the Earth was at the center, and the sun, moon, planets, and stars all moved in circular orbits around it. This geocentric view was widely accepted for many centuries. In ancient China, cosmology was also an important part of understanding the universe. the Chinese believed in a flat Earth covered by a hemispherical sky. They saw the universe as a series of concentric circles, with the Earth at the center. Chinese astronomers made careful observations of celestial events and developed a lunar calendar. They also created star maps and catalogued the stars and constellations. During the Middle Ages, the geocentric model of the universe remained dominant in Europe, largely due to the influence of the Catholic Church. However, in the Islamic world, scholars made significant advances in astronomy. Persian astronomer Al-Tusi developed a model that improved upon the Ptolemaic system, which was a refined version of Aristotle's geocentric model. Al-Tusi's work laid the groundwork for future astronomical discoveries. The Copernican revolution marked a major shift in our understanding of the universe. In the early 16th century, Polish astronomer Nicholas Copernicus proposed a heliocentric model in which the Sun was at the center of the universe and the Earth, along with other planets, orbited around it. This idea was revolutionary because it challenged the long-held geocentric view. Copernicus's model provided a simpler explanation for the observed motions of planets, which seemed to move in complex paths when viewed from a geocentric perspective. Despite its advantages, the Copernican model was not immediately accepted. Many people were reluctant to abandon the geocentric model, which was deeply ingrained in their worldview. However, over time, more evidence supported the heliocentric model. In the early 17th century, Johannes Kepler used precise observations to develop his laws of planetary motion, which described the orbits of planets as ellipses rather than perfect circles. Kepler's work provided strong support for the Copernican model. Italian astronomer Galileo Galilei also played a crucial role in advancing the heliocentric model. Using a telescope, he made several groundbreaking observations, such as the moons of Jupiter and the phases of Venus, which were consistent with the Copernican system. Galileo's findings challenged the traditional geocentric view and faced opposition from the Catholic Church. Despite this, his work laid the foundation for modern astronomy. The next major transformation in our understanding of the universe came with Albert Einstein's theories of relativity in the early 20th century. Einstein's special relativity, introduced in 1905, fundamentally changed our concepts of space and time. According to special relativity, the laws of physics are the same for all observers, regardless of their relative motion. This theory also introduced the idea that the speed of light is constant and cannot be exceeded. Special relativity led to the famous equation E equals mc squared, which shows that mass and energy are interchangeable. This had profound implications for our understanding of the universe, showing that energy could be converted into matter and vice versa. It also explained the behavior of objects moving at high speeds, close to the speed of light. In 1915, Einstein published his General Theory of Relativity, which further revolutionized our understanding of gravity. Instead of viewing gravity as a force between masses, general relativity described it as the curvature of space-time caused by the presence of mass and energy. Massive objects, like the Sun, bend the fabric of space-time, and this curvature affects the motion of other objects, like planets. General relativity provided new insights into the nature of the universe. It predicted phenomena such as the bending of light by gravity, known as gravitational lensing, and the existence of black holes, regions of space where gravity is so strong that not even light can escape. These predictions have been confirmed by observations, demonstrating the accuracy and power of Einstein's theory. Einstein's work also laid the groundwork for modern cosmology. It led to the understanding that the universe is dynamic and can expand or contract. In the 1920s, astronomer Edwin Hubble discovered that distant galaxies are moving away from us, indicating that the universe is expanding. This finding supported the Big Bang theory, which proposes that the universe began as a hot, dense point and has been expanding ever since. The expanding universe. In the 1920s, Edwin Hubble made a groundbreaking discovery that changed our understanding of the universe forever. Using powerful telescopes, he observed that distant galaxies were moving away from us. By measuring the light from these galaxies, Hubble found that the light was redshifted, meaning it shifted towards the red end of the spectrum. This redshift indicated that the galaxies were receding from us, much like the sound of a siren lowering in pitch as it moves away. Hubble's observations led to the realization that the universe is expanding. This was a radical idea at the time, challenging the notion that the universe was static and unchanging. The discovery that galaxies are moving away from each other suggested that the universe had a beginning from which it has been expanding ever since. This expansion is often compared to a balloon being blown up, with galaxies, like dots on the balloon's surface, moving apart as the balloon inflates. In the 1960s, further evidence for the expanding universe came with the discovery of the cosmic microwave background radiation. This faint glow of radiation, detectable in all directions, was first discovered by accident by scientists Arno Penzias and Robert Wilson. They noticed a persistent noise in their radio antenna, which turned out to be the afterglow of the Big Bang, the moment the universe began. The cosmic microwave background radiation is crucial evidence supporting the Big Bang theory. It is the remnant heat from the Big Bang, now cooled and stretched to microwave wavelengths due to the expansion of the universe. This radiation provides a snapshot of the universe when it was just 380,000 years old, a time when atoms first formed and the universe became transparent to light. By studying this radiation, scientists can learn about the early conditions of the universe and how it has evolved over billions of years. The idea that the universe is expanding from a hot, dense beginning raised questions about how this expansion started. To address these questions, scientists developed the theory of inflation. Inflation theory proposes that, a fraction of a second after the Big Bang, the universe underwent a period of extremely rapid expansion. During this brief moment, the universe expanded faster than the speed of light, growing exponentially from a tiny point to a vast region. Inflation explains several important features of the universe. First, it accounts for the uniformity of the cosmic microwave background radiation. Without inflation, it would be difficult to explain why the radiation is so uniform across the sky, given that distant regions of the universe would not have had time to exchange information or energy. Inflation suggests that these regions were once close together before being rapidly separated. Inflation also helps explain the large-scale structure of the universe. The theory predicts that tiny quantum fluctuations during inflation were stretched to macroscopic scales, seeding the formation of galaxies and clusters of galaxies. These fluctuations are observed as small temperature variations in the cosmic microwave background radiation. By studying these variations, scientists can learn about the conditions during inflation and the early universe's properties. The expanding universe and the theory of inflation have profound implications for our understanding of the cosmos. They suggest that the universe we see today, with its vast array of galaxies and complex structures, evolved from a simple uniform state through processes driven by the laws of physics. These discoveries also raise intriguing questions about the ultimate fate of the universe. If the expansion continues, will it go on forever, or will it eventually slow down and reverse, leading to a collapse? Modern observations indicate that the expansion of the universe is not slowing down, but accelerating. This acceleration is thought to be driven by a mysterious force called dark energy, which makes up about 70% of the universe's total energy. The nature of dark energy remains one of the biggest mysteries in cosmology, and understanding it could provide crucial insights into the fate of the universe. The journey from Hubble's discovery of the expanding universe to the development of inflation theory and the study of dark energy highlights the incredible progress in our understanding of the cosmos. The edge of the observable universe. The edge of the observable universe is defined by what we call the cosmic horizon. This horizon represents the furthest distance from which light has had time to reach us since the beginning of the universe. Because the universe is about 13.8 billion years old, the light from the most distant objects we can see has been traveling for 13.8 billion years. However, due to the expansion of the universe, these objects are now much farther away than 13.8 billion light-years. The cosmic horizon is like a giant bubble around us, with a radius of about 46.5 billion light-years. Anything beyond this bubble is currently unobservable, because its light hasn't had enough time to reach us. This doesn't mean that nothing exists beyond the horizon, it just means we can't see it yet. The concept of redshift is essential in understanding the cosmic horizon. When we look at distant galaxies, we see that their light is redshifted. This means the light waves have been stretched to longer wavelengths or towards the red end of the spectrum as the galaxies move away from us. The greater the redshift, the farther away the galaxy is, and the faster it is receding. By measuring the redshift of galaxies, we can determine their distances and how fast they are moving away, giving us a glimpse into the universe's expansion history. When we observe light from distant galaxies, we are actually looking back in time. Because light takes time to travel across space, we see distant objects as they were when the light left them, not as they are now. For example, when we observe a galaxy 10 billion light-years away, we see it as it was 10 billion years ago. This light travel time allows us to study the universe's past and understand its evolution over billions of years. The observable universe is only a portion of the entire universe. Beyond the cosmic horizon lies the unobservable universe, regions we can't see because their light hasn't reached us yet. The distinction between the observable and unobservable universe is crucial for several reasons. Firstly, it affects our understanding of the universe's size and structure. The observable universe is vast, but it's only a tiny fraction of the whole universe, which might be infinite. This means there could be countless galaxies, stars, and planets beyond what we can see, possibly even regions with different physical laws or properties. Secondly, the unobservable universe holds clues to the universe's overall shape and topology. Scientists use models and observations from the observable universe to infer what might lie beyond the horizon. These models help us understand whether the universe is flat, open, or closed, and how it might evolve in the future. Lastly, the distinction between the observable and unobservable universe has philosophical implications. It challenges our perception of reality and our place in the cosmos. Knowing that there are regions of the universe we will never see, no matter how advanced our technology becomes, reminds us of the limits of human knowledge and the vastness of the cosmos. Studying the edge of the observable universe also helps us understand the early stages of the universe. The light from the most distant galaxies comes from a time when the universe was very young. By analyzing this light, scientists can learn about the conditions and processes that occurred shortly after the Big Bang. This information helps refine our models of cosmic evolution and the formation of galaxies and large-scale structures. The study of the cosmic horizon and the observable universe connects to many other areas of cosmology and astrophysics. For example, it ties into the study of dark matter and dark energy, which make up most of the universe's mass and energy but remain largely mysterious. Understanding how these components influence the universe's expansion and structure helps us build a more complete picture of the cosmos. Philosophical implications of an infinite universe. The concept of infinity has fascinated humanity for centuries, extending its roots deep into the realms of both cosmology and mathematics. In cosmology, infinity often refers to the boundless nature of the universe. When we talk about the universe being infinite, we mean that it has no end, stretching out endlessly in all directions. This idea challenges our understanding, as our daily experiences are limited to finite spaces and objects. In mathematics, Infinity is more than just a theoretical concept. It is a well-defined idea with practical applications. Mathematicians use the symbol to represent infinity and have developed a rigorous framework for working with infinite quantities. Calculus, for instance, deals extensively with infinite series and limits, allowing us to approach the infinitely small and the infinitely large in a structured manner. Infinity in mathematics helps us grasp the ungraspable, providing tools to analyze and describe phenomena that seem beyond our finite comprehension. When we think about an infinite universe, it poses profound existential questions about humanity's place within it. In an infinite universe, the idea of a central or special location becomes meaningless. If space extends forever, then no point can be considered the center. This shifts our perspective from seeing Earth, and by extension ourselves, as the focal point of existence, to being just a tiny part of an immense, perhaps incomprehensible, expanse. This can be both humbling and disconcerting. The notion that we are not unique, but rather a small part of an infinite tapestry, challenges our sense of importance and significance in the cosmos. Moreover, the concept of an infinite universe brings into question the nature of existence itself. If the universe is infinite, then it may contain infinite versions of ourselves and our lives, slightly altered in myriad ways. This idea, often explored in science fiction, suggests a multiverse where every possible outcome exists somewhere. While this is speculative, it invites us to ponder the limits of reality and our perception of it. Could there be countless versions of our world, each slightly different from the one we know? If so, what does that mean for our understanding of identity and individuality? These considerations lead us to the anthropic principle, a philosophical idea that asserts the observations of the universe must be compatible with the conscious life that observes it. There are two main interpretations of the anthropic principle: the weak and the strong anthropic principles. The weak anthropic principle suggests that the universe's observed values of physical constants are not random. Rather, they fall within the narrow range that allows for the existence of life. If these constants were even slightly different, life as we know it could not exist, and therefore we would not be here to observe them. The strong anthropic principle goes a step further, proposing that the universe must have properties that inevitably lead to the development of conscious life. This implies a universe somehow designed with the emergence of observers in mind. This interpretation raises profound questions about the nature of reality and the possibility of a purposeful design behind the cosmos. The anthropic principle provides a framework for understanding why the universe is the way it is, despite its apparent fine-tuning. In an infinite universe, the anthropic principle can help explain why we find ourselves in a region where conditions are just right for life. If there are infinite regions with varying conditions, then it is inevitable that some regions will have the right conditions for life to emerge. We happen to be in one of those regions, not because it is special or unique, but because it is one of the few where observers like us could exist. However, the anthropic principle is not without its critics. Some argue that it is a tautology, a statement that is true by necessity but provides no explanatory power. Others contend that it borders on teleological explanations, implying purpose or design in the universe's structure. Despite these criticisms, the anthropic principle remains a valuable tool for exploring the philosophical implications of our existence in an infinite cosmos. As we delve deeper into the philosophical implications of an infinite universe, we encounter questions about the nature of reality itself. If the universe is truly infinite, then every possible event, no matter how unlikely, must happen somewhere. This raises the question of free will and determinism. In a deterministic universe, every event is the result of preceding events, governed by the laws of physics. In an infinite universe with infinite possibilities, does free will truly exist? Or are we merely following one of countless predetermined paths? Additionally, the infinite nature of the universe forces us to reconsider our understanding of time. If space is infinite, then time too may be boundless. The concept of an eternal universe challenges our linear perception of time, where events have a beginning and an end. In an infinite timeline, the past, present, and future may all coexist in a manner that defies our conventional understanding. This could imply that our existence is but a fleeting moment in an endless continuum, adding another layer to the philosophical exploration of infinity. The idea of an infinite universe also intersects with questions of meaning and purpose. If the universe is infinite and contains countless worlds, does our individual life hold any intrinsic meaning? Some might find this prospect daunting, feeling insignificant in the grand scheme of things. Others may find comfort in the idea that we are part of something much larger, a vast and interconnected web of existence. This duality mirrors the broader human experience, where we constantly seek meaning in a world that often seems indifferent to our existence. We must also consider the role of science in addressing these profound questions. Science provides us with tools to explore and understand the universe, but it also has its limits. While we can develop theories and models to describe the infinite, our finite minds and tools can only grasp so much. This intersection of science and philosophy highlights the importance of interdisciplinary approaches to understanding the cosmos. By combining scientific inquiry with philosophical reflection, we can gain a more nuanced understanding of our place in the universe. Ultimately, the concept of an infinite universe invites us to embrace the unknown. Multiverse theories. When we delve into multiverse theories, we're venturing into some of the most intriguing and complex ideas in modern physics. These theories suggest that our universe might not be the only one. Instead, it could be just one of countless others, each with its own distinct properties and laws of physics. This concept expands our understanding of reality far beyond what we can observe and measure. String theory is one of the most prominent frameworks in physics that suggests the possibility of multiple universes. At its core, string theory proposes that the fundamental building blocks of the universe are not particles but tiny vibrating strings of energy. These strings can vibrate at different frequencies, and their vibrations determine the properties of particles. String theory attempts to unify all the fundamental forces of nature, including gravity, into a single theoretical framework. One of the remarkable aspects of string theory is that it requires more than the familiar 3 dimensions of space and one of time. It suggests that there could be as many as 10 or 11 dimensions. Most of these extra dimensions are thought to be compactified or curled up, so small that we can't perceive them. However, in some versions of string theory, these extra dimensions could lead to the existence of parallel universes. Each of these universes might have different physical properties, and they could be entirely separate from our own. Parallel universes are a natural outcome of string theory's mathematical structure. In this view, our universe is just one of many possible universes, each with its own unique set of physical laws. These parallel universes could be incredibly diverse, with different forms of matter, energy, and even different dimensions. The idea of parallel universes stretches our imagination and challenges our understanding of what reality truly is. Another fascinating idea is that of bubble universes. This concept comes from the theory of cosmic inflation, which suggests that the early universe underwent a rapid expansion, growing exponentially in a fraction of a second. According to this theory, different regions of space could have stopped inflating at different times, creating distinct bubbles of space-time. Each of these bubbles could form a separate universe with its own properties and physical laws. These bubble universes are thought to be non-interacting, meaning they don't influence each other. They exist in their own regions of space, separated by vast distances, or perhaps even by different dimensions. The idea of bubble universes implies that there could be countless other universes, each with its own unique characteristics. Some of these universes might be similar to ours, while others could be drastically different, with entirely different forms of matter and energy. The concept of bubble universes helps us to understand how the multiverse might be structured. It suggests that our universe is just one bubble in a vast cosmic foam, with other bubbles constantly forming and evolving. This idea expands our understanding of the cosmos and challenges us to think beyond the confines of our observable universe. The many worlds interpretation of quantum mechanics is another compelling multiverse theory. Quantum mechanics is the branch of physics that deals with the behavior of particles on the smallest scales. It is known for its counterintuitive and often bizarre predictions. One of the fundamental principles of quantum mechanics is that particles can exist in multiple states simultaneously, a phenomenon known as superposition. According to the many worlds interpretation, every time a quantum event occurs, the universe splits into multiple parallel worlds. Each of these worlds represents a different outcome of the quantum event. For example, if a particle can be in two places at once, the universe splits into two parallel worlds, one where the particle is in one place and another where it is in the other place. This process of splitting happens constantly, creating a vast number of parallel worlds. In the many worlds interpretation, every possible outcome of every event exists in its own parallel world. This means that there are countless versions of reality, each slightly different from the others. Some of these parallel worlds might be very similar to our own, while others could be radically different. The many worlds interpretation challenges our understanding of reality and raises profound questions about the nature of existence. The idea of parallel worlds in quantum mechanics is both fascinating and perplexing. It suggests that the universe is constantly branching into multiple parallel realities, each with its own version of events. This concept challenges our perception of time and causality, as it implies that every possible future exists simultaneously in different parallel worlds. These multiverse theories, string theory's parallel universes, the bubble universes from cosmic inflation, and the many worlds interpretation of quantum mechanics all suggest that our universe might be just one of many. They expand our understanding of the cosmos and challenge us to think beyond the limits of our observable universe. The idea of a multiverse raises profound philosophical questions about the nature of reality, our place in the cosmos, and the fundamental laws that govern existence. These theories not only expand our understanding of the cosmos, but also invite us to consider the profound implications of a multiverse. If multiple universes exist, each with its own unique properties, what does this mean for our understanding of reality? How do we reconcile the existence of parallel worlds with our everyday experiences? These questions challenge us to think deeply about the nature of existence and the limits of human knowledge. The exploration of multiverse theories is a testament to the power of human curiosity and imagination. It demonstrates our willingness to question the boundaries of our understanding and to seek answers to some of the most profound questions about the universe. Black holes and beyond. Black holes are among the most mysterious and intriguing objects in the universe. They are regions of space where gravity is so strong that nothing, not even light, can escape. The boundary around a black hole, beyond which nothing can return, is called the event horizon. The event horizon marks the point of no return. Once something crosses this boundary, it is inevitably pulled into the black hole. The event horizon is not just a physical boundary, but also a philosophical one. It represents the limits of our ability to observe and understand what happens inside a black hole. Once an object crosses the event horizon, it is forever hidden from our view. This challenges our understanding of reality because it means there are regions of the universe that are fundamentally inaccessible to us. The existence of event horizons forces us to confront the limitations of human knowledge and the boundaries of what we can observe and understand. Stephen Hawking made significant contributions to our understanding of black holes, particularly through his theory of Hawking radiation. Before Hawking's work, black holes were thought to be completely black, with no way for anything to escape their gravitational pull. However, Hawking showed that black holes could emit radiation due to quantum effects near the event horizon. This radiation, now known as Hawking radiation, results from the interaction between the black hole and the quantum vacuum. Hawking radiation has profound implications for our understanding of black holes. It suggests that black holes are not entirely black, and that they can lose mass and energy over time. Eventually, a black hole could evaporate completely through the emission of Hawking radiation. This process challenges the traditional view of black holes as eternal and unchanging objects. Instead, it suggests that black holes are dynamic and evolving, constantly interacting with their surroundings. One of the most perplexing mysteries associated with black holes is the information paradox. In physics, information refers to the complete description of the state of a physical system. According to the principles of quantum mechanics, information should always be preserved, even when it is transformed or hidden. However, the existence of black holes poses a challenge to this principle. When an object falls into a black hole, the information about its state seems to be lost forever beyond the event horizon. If the black hole eventually evaporates through Hawking radiation, it would appear that the information is permanently lost, which violates the principle of information preservation. This creates a paradox. Either the information is somehow preserved, or our understanding of quantum mechanics needs to be revised. The information paradox has been a subject of intense debate and research among physicists. Several possible solutions have been proposed, but none have been universally accepted. One idea is that the information is encoded in the Hawking radiation itself, although this remains a topic of ongoing investigation. Another proposal is that the information is preserved in a holographic surface surrounding the black hole, a concept known as the holographic principle. The information paradox highlights the profound challenges that black holes pose to our understanding of the universe. It suggests that there are fundamental aspects of reality that we do not yet fully comprehend. The resolution of the information paradox could lead to significant advancements in our understanding of quantum mechanics and the nature of the universe. Black holes also raise important questions about the nature of space and time. Near the event horizon, the effects of gravity are so extreme that they distort the fabric of space-time. Time appears to slow down as an object approaches the event horizon, eventually coming to a complete stop at the horizon itself. This means that an observer falling into a black hole would experience time very differently from an outside observer. The extreme conditions near black holes provide a unique laboratory for testing the laws of physics. They offer insights into the behavior of matter and energy under the most extreme conditions, and they challenge our understanding of the fundamental nature of reality. Studying black holes helps us to probe the limits of our knowledge and to explore the frontiers of modern physics. Beyond the event horizon lies the singularity, a point where the gravitational forces become infinitely strong and the curvature of space-time becomes infinite. The singularity represents a breakdown of our current understanding of physics. The laws of general relativity, which describe the behavior of gravity, no longer apply in the extreme conditions of the singularity. This indicates that our current theories are incomplete and that a new, more comprehensive theory of gravity is needed. The search for a theory that can describe the behavior of gravity at the singularity is one of the major goals of modern physics. Such a theory, often referred to as quantum gravity, would unify the principles of quantum mechanics and general relativity. It would provide a complete description of the behavior of matter and energy under the most extreme conditions, and could offer new insights into the nature of space and time. The study of black holes has already led to significant advancements in our understanding of the universe. It has revealed the existence of phenomena that challenge our conventional understanding of reality and has opened up new avenues of research. As we continue to explore the mysteries of black holes, we are likely to uncover new and surprising insights into the nature of the universe and our place within it. Black holes also have implications for our understanding of cosmology and the evolution of the universe. They are thought to play a crucial role in the formation and evolution of galaxies. Supermassive black holes, which are millions or billions of times more massive than the Sun, are found at the centers of most galaxies, including our own Milky Way. These black holes influence the dynamics of their host galaxies and are thought to have a significant impact on their formation and evolution. The study of black holes also raises important questions about the fate of the universe. If black holes can evaporate through Hawking radiation, what does this mean for the long-term evolution of the universe? Will all black holes eventually evaporate, leaving behind a universe filled with radiation and elementary particles? These questions challenge our understanding of the ultimate fate of the universe and the nature of time itself. The exploration of black holes and their mysteries is a testament to the power of human curiosity and the drive to understand the universe. It demonstrates our willingness to confront the unknown and to seek answers to some of the most profound questions about the nature of reality. Through the study of black holes, we are constantly pushing the boundaries of our knowledge and expanding our understanding of the cosmos. In the quest to understand black holes, we are not only seeking answers to specific scientific questions, but also exploring the deeper philosophical implications of our existence. The study of black holes forces us to confront the limits of our understanding and to consider the fundamental nature of reality. It challenges us to think deeply about the nature of space, time, and information, and to explore the profound mysteries that lie at the heart of the universe. Through the study of black holes, we gain a deeper appreciation for the mystery and wonder of the universe. Theories of everything. The search for a unified theory, often referred to as a theory of everything, represents one of the most ambitious and profound quests in modern physics. This pursuit aims to reconcile the two most successful frameworks of 20th century physics, quantum mechanics and general relativity. Quantum mechanics describes the behavior of particles at the smallest scales, while general relativity explains the force of gravity and the structure of space and time at the largest scales. However, these two theories are fundamentally incompatible with each other, and a unified theory seeks to bridge this gap. Quantum mechanics is extraordinarily successful in explaining the behavior of particles and forces at the atomic and subatomic levels. It describes a world where particles can exist in multiple states simultaneously, where they can be entangled over vast distances, and where probabilities govern outcomes. This theory has led to numerous technological advancements, from semiconductors to MRI machines, yet when applied to the gravitational field, quantum mechanics struggles. Gravity, as described by general relativity, behaves in ways that quantum theory cannot easily account for. General relativity, proposed by Albert Einstein, revolutionized our understanding of gravity by describing it as a curvature of space-time caused by mass and energy. This theory accurately predicts the motion of planets, the bending of light by gravity, and the dynamics of the universe at large scales. However, it does not incorporate the principles of quantum mechanics, which govern the microscopic realm. As a result, the two theories produce conflicting predictions when applied to conditions where both quantum effects and strong gravitational fields are significant, such as inside black holes or during the Big Bang. String theory emerged as a promising candidate for a unified theory. It proposes that the fundamental building blocks of the universe are not point-like particles, but tiny vibrating strings. These strings can vibrate at different frequencies, and each frequency corresponds to a different particle. String theory naturally includes gravity and can potentially reconcile it with quantum mechanics. By treating particles as one-dimensional objects rather than zero-dimensional points, string theory smooths out many of the infinities and inconsistencies that arise when trying to merge the two frameworks. String theory also introduces additional dimensions beyond the familiar 3 dimensions of space and 1 of time. These extra dimensions are compactified, meaning they are curled up so tightly that they are not observable at everyday scales. The mathematics of string theory suggests that there could be as many as 10 or 11 dimensions. These hidden dimensions provide the necessary framework for unifying all fundamental forces, including gravity, electromagnetism, and the strong and weak nuclear forces. M-theory is an extension of string theory that unifies the 5 different versions of string theory into a single framework. It suggests that the fundamental objects in the universe are not just strings, but also higher dimensional membranes, or branes. These branes can have various dimensions, and our universe could be one such 3-dimensional brane floating in a higher dimensional space. M-theory provides a more comprehensive picture and is considered a leading candidate for a theory of everything. Despite its elegance and potential, string theory and M-theory face significant challenges. One of the main issues is that they are difficult to test experimentally. The scales at which string effects become significant are so small, and the energies required to probe them are so high that they are beyond the reach of current technology. Additionally, string theory predicts a vast landscape of possible solutions, corresponding to different possible universes with different physical properties. This makes it challenging to identify which, if any, of these solutions corresponds to our universe. An alternative approach to unifying quantum mechanics and general relativity is loop quantum gravity. This theory takes a different path by attempting to quantize spacetime itself. Instead of treating gravity as a force within a fixed spacetime background, loop quantum gravity suggests that spacetime is made up of discrete, quantized loops. These loops are incredibly small, on the order of the Planck length, which is about 10 circumflex 35 meters. At this scale, the smooth fabric of spacetime breaks down into a network of finite loops. Loop quantum gravity aims to preserve the principles of general relativity while incorporating the quantization methods of quantum mechanics. One of the key achievements of this theory is the derivation of a discrete structure of space, where space itself is composed of finite loops or quanta of space. This discrete nature could help resolve the infinities that plague quantum gravity calculations. Loop quantum gravity also provides insights into the nature of black holes, suggesting that the singularities predicted by general relativity are replaced by finite, quantized structures. Another significant contribution of loop quantum gravity is its potential explanation for the Big Bang. According to this theory, the Big Bang was not the beginning of time, but rather a transition from a previous contracting phase to our current expanding phase. This idea, known as the Big Bounce, implies a cyclic model of the universe, where each cycle begins with a bounce rather than a singularity. This perspective provides a new way of thinking about the origins and evolution of the universe. Loop quantum gravity and string theory represent 2 different but complementary approaches to understanding the fundamental nature of the universe. While string theory attempts to unify all fundamental forces through the vibrations of strings and higher dimensional branes, loop quantum gravity focuses on the quantization of spacetime itself. Both theories offer profound insights and face significant challenges, and it is possible that the true theory of everything will incorporate elements of both approaches. The search for a unified theory is not just a quest for a set of equations that describe all physical phenomena. It is also a journey to understand the deepest principles that govern the universe. It challenges us to rethink our assumptions about space, time, and matter, and to explore the fundamental nature of reality. The pursuit of a theory of everything reflects our innate desire to find order and coherence in the cosmos, to uncover the underlying unity that connects all things. As we continue to explore these theories, we are reminded of the power of human curiosity and the drive to understand the universe. The search for a unified theory pushes the boundaries of our knowledge and challenges us to think beyond the limits of our current understanding. It invites us to explore the mysteries of the cosmos with an open mind and a sense of wonder, to seek answers to the most profound questions about the nature of reality. The journey toward a theory of everything is ongoing, and each step brings new insights and challenges. Whether through the elegant mathematics of string theory, the discrete structures of loop quantum gravity, or some other yet-to-be-discovered framework, the pursuit of a unified theory represents the pinnacle of human intellectual achievement. It is a testament to our enduring quest to understand the universe and our place within it. Through the study of string theory, loop quantum gravity, and other approaches, we gain a deeper appreciation for the interconnectedness of all things. We are reminded that the quest for knowledge is an ongoing journey, one that requires creativity, perseverance, and a willingness to embrace the unknown. Cosmic structures and dark matter. When we look at the universe on a grand scale, we see a remarkable tapestry of cosmic structures. Galaxies, clusters, and superclusters form a complex web, revealing the vastness and interconnectedness of the cosmos. Galaxies are the fundamental building blocks, each containing billions of stars, planets, and other celestial objects bound together by gravity. Our own Milky Way is one of these immense star systems, spiraling gracefully through space. Galaxies do not exist in isolation. They are grouped into clusters which can contain hundreds or even thousands of galaxies. These clusters are gravitationally bound, meaning that the galaxies within them orbit a common center of mass. The interaction between galaxies within clusters often leads to spectacular phenomena such as galaxy collisions and the formation of new stars. Even larger than clusters are superclusters, which are vast assemblies of galaxy clusters. These enormous structures are among the largest known in the universe, stretching across hundreds of millions of light-years. Superclusters form a cosmic web, with filaments of galaxies and clusters connected by vast voids of empty space. This web-like structure is the result of billions of years of gravitational interactions and the expansion of the universe. One of the most intriguing aspects of the large-scale structure of the universe is that much of it is invisible to us. This brings us to the concepts of dark matter and dark energy, which together make up most of the universe. Despite their names, these components are not directly observable because they do not emit, absorb, or reflect light. However, their presence is inferred from their gravitational effects on visible matter, radiation, and the large-scale structure of the universe. Dark matter is believed to make up about 27% of the universe's total mass and energy content. It does not interact with electromagnetic forces, which means it doesn't emit light or energy that we can detect with current instruments. However, we can observe its gravitational effects on galaxies and clusters of galaxies. For example, galaxies rotate faster than can be accounted for by the visible matter alone. The additional gravitational pull needed to explain this rotation is attributed to dark matter. Without it, galaxies would not hold together as they do. Dark matter is thought to form a scaffolding for the universe. It clumps together under gravity, creating the seeds for galaxy formation. As ordinary matter falls into these dark matter clumps, galaxies are born. This invisible framework helps explain the distribution and movement of galaxies and clusters we observe today. Dark energy is even more mysterious. It is thought to make up about 68% of the universe and is responsible for its accelerated expansion. This expansion was first observed in the late 20th century when astronomers discovered that distant galaxies were moving away from us faster than expected. Dark energy acts as a repulsive force, counteracting the pull of gravity and causing the universe to expand at an increasing rate. Despite its profound effects on the cosmos, the nature of dark energy remains one of the biggest mysteries in cosmology. The lambda CDM model is the standard model of Big Bang cosmology. Lambda refers to the cosmological constant, which represents dark energy in Einstein's field equations of general relativity. CDM stands for cold dark matter, which refers to dark matter particles that move slowly compared to the speed of light. This model provides a comprehensive framework for understanding the evolution and structure of the universe from its earliest moments to the present day. According to the lambda CDM model, the universe began with the Big Bang, a rapid expansion from an extremely hot and dense state about 13.8 billion years ago. As the universe expanded, it cooled, allowing particles to form atoms and eventually leading to the formation of stars and galaxies. The model explains the observed large-scale structure of the universe, the cosmic microwave background radiation, and the abundance of light elements, such as hydrogen and helium. The lambda CDM model also accounts for the accelerated expansion of the universe due to dark energy. It provides a framework for understanding how dark matter influences the formation and evolution of cosmic structures. Despite its successes, the model is not without its challenges. For example, the exact nature of dark matter and dark energy remains unknown, and there are discrepancies between the model's predictions and certain observations, such as the rate of cosmic expansion. Studying the large-scale structure of the universe and the role of dark matter and dark energy requires sophisticated tools and techniques. Observations from ground-based telescopes, space-based observatories, and cosmic microwave background experiments all contribute to our understanding. These observations allow scientists to map the distribution of galaxies, measure the effects of dark matter and dark energy, and test the predictions of the lambda CDM model. One of the key tools in this research is the cosmic microwave background (CMB) radiation. The CMB is the afterglow of the Big Bang, a faint radiation that fills the universe and provides a snapshot of the universe when it was just 380,000 years old. By studying the CMB, scientists can learn about the early universe's conditions and the distribution of matter and energy. The detailed measurements of the CMB made by missions, such as the Planck satellite, have provided strong support for the lambda CDM model. Another important area of research is the study of galaxy clusters. These massive structures are influenced by both dark matter and dark energy, making them valuable probes of the universe's composition and evolution. Observations of galaxy clusters, including their distribution, motion, and interaction with the surrounding environment, help scientists understand the effects of dark matter and dark energy on cosmic structures. Gravitational lensing is another powerful technique used to study dark matter. When light from a distant galaxy passes near a massive object like a galaxy cluster, it is bent by the object's gravity. This bending creates distorted or multiple images of the background galaxy, an effect known as gravitational lensing. By analyzing these distortions, scientists can map the distribution of dark matter in the lensing object, providing insights into its properties and behavior. The study of large-scale cosmic structures, dark matter, and dark energy is a rapidly evolving field. New discoveries and advancements in technology continue to push the boundaries of our understanding. Future missions, such as the James Webb Space Telescope and the European Space Agency's Euclid mission, promise to provide even more detailed observations of the universe, shedding light on its most fundamental mysteries. We are reminded of the complexity and interconnectedness of the cosmos. These invisible components play crucial roles in shaping the universe we see today, influencing everything from the formation of galaxies to the expansion of the universe itself. The quest to understand these cosmic mysteries drives us to develop new technologies, refine our theories, and expand our knowledge of the universe. The lambda CDM model, with its inclusion of dark matter and dark energy, provides a robust framework for understanding the universe's evolution and structure. It highlights the importance of these unseen components in shaping the cosmos and challenges us to delve deeper into their nature. As we continue to study the universe, we are likely to uncover new insights and refine our models, bringing us closer to a more complete understanding of the cosmos. The exploration of cosmic structures and the roles of dark matter and dark energy is a testament to human curiosity and the drive to understand the universe. It reminds us that the universe is far more complex and mysterious than we might have imagined. By studying these fundamental aspects of the cosmos, we not only learn about the universe's past and present, but also gain insights into its future, and our place within it. The role of observers in the universe. The role of observers in the universe touches on some of the most intriguing and debated topics in modern science and philosophy. The participatory anthropic principle suggests that observers are not just passive entities within the universe, but are crucial for its existence. This idea challenges the traditional view of the universe as a detached, objective reality, and instead posits that the act of observation is fundamental to the existence and nature of the universe. The participatory anthropic principle builds on the anthropic principle, which states that the universe must be compatible with the conscious beings that observe it. The participatory version goes further, suggesting that the universe requires observers to bring it into being. This idea was notably championed by physicist John Archibald Wheeler, who proposed that the act of observation could influence the very nature of reality. In this view, the universe is not fully realized until it is observed, and observers play an active role in shaping the cosmos. This principle implies that the presence of observers is essential for the universe to manifest its properties. Without conscious beings to observe and measure it, the universe's potential states remain unrealized. This concept challenges our understanding of existence, suggesting that reality is not fixed and independent, but is instead dynamically linked to the act of observation. Quantum mechanics further deepens our understanding of the relationship between observers and the universe. One of the most famous and puzzling aspects of quantum mechanics is the role of observation in determining the state of a quantum system. In the quantum realm, particles exist in a state of superposition, meaning they can be in multiple states at once. However, when an observation or measurement is made, the superposition collapses into a single, definite state. This phenomenon is known as wave function collapse. The classic example of this is the double-slit experiment, where particles such as electrons are fired at a barrier with two slits. If no one observes the particles, they behave like waves, creating an interference pattern on a screen behind the barrier. However, if an observer measures which slit the particles pass through, they behave like particles, and the interference pattern disappears. This experiment illustrates that the act of observation fundamentally alters the behavior of quantum systems. The idea that observation affects the state of quantum systems has profound implications for our understanding of reality. It suggests that the universe at the quantum level is not deterministic, but is influenced by the presence of observers. This challenges the classical view of an objective, observer-independent reality, and implies that consciousness plays a critical role in shaping the universe. The connection between consciousness and the universe is a topic of ongoing exploration and debate. Some scientists and philosophers propose that consciousness is a fundamental aspect of the universe, on par with matter and energy. This view suggests that consciousness is not merely a byproduct of complex physical processes, but is instead a basic component of reality. One perspective is that consciousness and the universe are intertwined in a way that cannot be fully understood through traditional scientific methods. This idea resonates with certain interpretations of quantum mechanics, where the observer's role is crucial in determining the outcome of events. If consciousness is indeed fundamental to the universe, it could mean that the universe is, in some sense, conscious, or that consciousness permeates all levels of reality. Another perspective explores the possibility that the universe is fine-tuned for the emergence of consciousness. The physical constants and laws of nature appear to be precisely calibrated to allow for the existence of life, and by extension, conscious beings. This fine-tuning has led some to speculate that consciousness is an integral part of the universe's design, suggesting a deeper connection between the cosmos and the conscious beings that inhabit it. Exploring the relationship between consciousness and the universe invites us to consider the nature of awareness itself. Consciousness is often viewed as a mysterious and elusive phenomenon, one that defies easy explanation. By examining its connection to the universe, we may gain new insights into both the nature of consciousness and the fundamental workings of the cosmos. The participatory anthropic principle, quantum mechanics, and the exploration of consciousness all point to a profound interconnectedness between observers and the universe. These ideas challenge our conventional understanding of reality and invite us to rethink the nature of existence. They suggest that the universe is not a static, objective entity, but is instead deeply influenced by the presence and actions of conscious beings. The role of observers highlights the dynamic and participatory nature of reality, where consciousness and the cosmos are inextricably linked. This interconnectedness invites us to explore the universe not just as passive observers, but as active participants in the unfolding of reality. The exploration of the role of observers in the universe is a journey into the heart of some of the most profound questions about existence. It challenges us to consider the nature of reality, the influence of consciousness, and the fundamental principles that govern the cosmos. Through this exploration, we gain a deeper appreciation for the intricate and mysterious ways in which the universe and consciousness are intertwined. The study of the participatory anthropic principle, quantum mechanics, and consciousness invites us to expand our horizons and explore the depths of reality. It challenges us to embrace the unknown and to consider the possibility that the universe is far more interconnected and dynamic than we ever imagined. In this quest, we are reminded of the power of human curiosity and the drive to understand the universe. The role of observers in the cosmos highlights the profound impact of consciousness on reality, inviting us to explore the fundamental principles that shape our existence. As we continue to study these ideas, we are likely to uncover new insights and deepen our understanding of the universe and our place within it. The observer effect. One of the most intriguing and perplexing phenomena in quantum mechanics is the observer effect. This effect fundamentally challenges our classical understanding of reality by suggesting that the mere act of observation can alter the state of a quantum system. At its core, the observer effect highlights the intimate relationship between measurement, observation, and the nature of reality itself. Quantum mechanics describes the behavior of particles at the smallest scales, where the principles of classical physics no longer apply. In this realm, particles can exist in multiple states simultaneously, a phenomenon known as superposition. For example, an electron can be in a state where it is simultaneously in two different places, or it can have multiple possible energies at the same time. However, when a measurement is made, this superposition collapses into a single definite state. This process is known as wave function collapse. The double-slit experiment is a classic demonstration of the observer effect in action. In this experiment, particles such as electrons or photons are fired at a barrier with two slits. If no one observes the particle's path, they behave like waves, creating an interference pattern on a screen behind the barrier. This pattern indicates that each particle passes through both slits simultaneously, interfering with itself. However, if an observer measures which slit the particles pass through, the particles behave like particles, not waves, and the interference pattern disappears. Instead, two distinct bands appear on the screen, corresponding to the two slits. The double-slit experiment illustrates that the act of observation fundamentally alters the behavior of quantum systems. When unobserved, particles exhibit wave-like behavior, existing in a superposition of states. But when observed, they behave like particles, with well-defined positions and trajectories. This phenomenon raises profound questions about the nature of reality and the role of consciousness in the universe. One interpretation of the observer effect is rooted in the Copenhagen interpretation of quantum mechanics, developed by Niels Bohr and Werner Heisenberg in the early 20th century. According to this interpretation, a quantum system exists in a superposition of states until it is measured. The act of measurement forces the system to choose one of its possible states, collapsing the wave function into a single outcome. This implies that the properties of a quantum system are not determined until they are observed. The Copenhagen interpretation suggests that reality at the quantum level is inherently probabilistic and that observation plays a crucial role in determining the outcome of quantum events. This challenges the classical view of an objective reality that exists independently of our observations. Instead, it posits that the act of observation is an integral part of the process, influencing the state of the system being observed. Another interpretation of the observer effect is the many worlds interpretation, proposed by Hugh Everett in 1957. According to this interpretation, every possible outcome of a quantum event actually occurs, but in separate, parallel universes. When a measurement is made, the universe splits into multiple branches, each corresponding to a different outcome. In this view, the observer effect does not collapse the wave function but instead results in the creation of multiple parallel realities. The many worlds interpretation eliminates the need for wave function collapse, suggesting that all possible outcomes exist simultaneously in a vast multiverse. While this interpretation provides a deterministic framework for understanding quantum mechanics, it also implies the existence of an almost unimaginable number of parallel universes, each with its own version of reality. This idea challenges our conventional understanding of existence and raises profound questions about the nature of reality and our place within it. The role of consciousness in the observer effect is a topic of ongoing debate and exploration. Some interpretations suggest that consciousness itself plays a fundamental role in collapsing the wave function. This idea, often associated with the work of physicist Eugene Wigner and others, posits that the mind of the observer is essential for bringing about a definite outcome in a quantum measurement. According to this view, consciousness is not just a passive observer, but an active participant in the creation of reality. This perspective challenges the traditional scientific view that consciousness is merely a byproduct of physical processes. Instead, it suggests that consciousness is a fundamental aspect of the universe, playing a crucial role in the manifestation of physical reality. If consciousness is indeed essential for collapsing the wave function, it implies that the mind has a direct influence on the fabric of reality itself. The connection between consciousness and the observer effect has led to various philosophical and speculative ideas. One such idea is the participatory anthropic principle, which suggests that the universe requires observers to bring it into being. This principle, championed by physicist John Archibald Wheeler, posits that the act of observation is essential for the universe to manifest its properties. In this view, reality is not fixed and objective, but is dynamically linked to the presence of conscious observers. The participatory anthropic principle implies a profound interconnectedness between consciousness and the cosmos. It suggests that the universe is not a passive backdrop, but an active, participatory reality that depends on the presence of observers. This idea challenges our conventional understanding of existence and invites us to consider the possibility that consciousness plays a fundamental role in shaping the universe. The observer effect also has practical implications for the development of quantum technologies. Quantum computing, for example, relies on the principles of superposition and entanglement to perform calculations that are beyond the reach of classical computers. In a quantum computer, qubits, quantum bits, can exist in multiple states simultaneously, allowing for parallel processing of information. However, the act of measuring a qubit collapses its superposition, making it challenging to extract information without disrupting the computation. Quantum cryptography is another area where the observer effect plays a crucial role. Quantum key distribution (QKD) protocols, such as the BB84 protocol, leverage the principles of quantum mechanics to create secure communication channels. In QKD, any attempt to eavesdrop on the communication introduces disturbances that can be detected by the legitimate parties. This is because the act of observing the quantum states used to encode information alters those states, revealing the presence of an eavesdropper. The observer effect thus provides a foundation for the security of quantum communication, ensuring that any unauthorized observation can be detected. This has significant implications for the development of secure communication networks and the protection of sensitive information. Beyond its practical applications, the observer effect invites us to explore deeper philosophical questions about the nature of reality and the role of consciousness. It challenges the classical view of an objective, observer-independent universe and suggests that observation is an integral part of the process that brings reality into being. This perspective invites us to consider the possibility that reality is not fixed and static, but is dynamically linked to the presence of conscious beings. Technological advances in cosmology. Technological advances in cosmology have dramatically expanded our understanding of the universe. Telescopes and observatories, both ground-based and space-based, have allowed us to peer deeper into space and time, uncovering the secrets of the cosmos. These instruments have evolved over the years, becoming more powerful and sophisticated, enabling astronomers to make groundbreaking discoveries. Telescopes are the primary tools for observing the universe. The first telescopes, built in the early 17th century, used simple lenses to magnify the light from distant objects. These early telescopes allowed astronomers like Galileo Galilei to make significant discoveries, such as the moons of Jupiter and the phases of Venus. As technology advanced, telescopes grew larger and more powerful. Reflecting telescopes, which use mirrors instead of lenses, were developed in the 18th century and allowed for even greater magnification and clarity. In the 20th century, the development of radio telescopes opened a new window on the universe. Radio telescopes detect radio waves emitted by celestial objects, providing information that is not visible in optical light. This technology has led to the discovery of phenomena such as pulsars, quasars, and the cosmic microwave background radiation, which is the afterglow of the Big Bang. Space-based telescopes have revolutionized our view of the universe by overcoming the limitations of Earth's atmosphere. The atmosphere can distort and block certain wavelengths of light, making it difficult to observe celestial objects with ground-based telescopes. Space telescopes, positioned above the atmosphere, provide a clear and unobstructed view of the cosmos. The Hubble Space Telescope, launched in 1990, has been one of the most significant space missions in the history of astronomy. Hubble has provided stunning images of distant galaxies, nebulae, and other celestial objects, transforming our understanding of the universe. It has helped to measure the rate of expansion of the universe, provided evidence for the existence of dark energy, and contributed to our knowledge of star formation and the life cycles of stars. Hubble's observations have led to thousands of scientific papers and numerous discoveries. Building on Hubble's legacy, the James Webb Space Telescope, JWST, represents the next generation of space observatories. Scheduled for launch in December 2021, JWST is designed to observe the universe in the infrared spectrum, which will allow it to see through dust clouds and study the formation of stars and planets. JWST's powerful instruments will enable it to look back in time to the first galaxies that formed after the Big Bang, providing insights into the early universe. Its advanced technology and larger mirror will make it one of the most powerful telescopes ever built, capable of making discoveries that were previously unimaginable. Other significant space missions have also contributed to our understanding of the universe. The Planck satellite, launched in 2009, has mapped the cosmic microwave background radiation with unprecedented precision, providing detailed information about the early universe and the fundamental parameters of cosmology. The Kepler Space Telescope, launched in 2009, has discovered thousands of exoplanets, expanding our knowledge of planetary systems beyond our own. Future prospects for space missions and observatories hold great promise for furthering our understanding of the cosmos. The upcoming European Space Agency's Euclid mission, scheduled for launch in 2022, will map the geometry of the dark universe, studying dark matter and dark energy with high precision. Euclid will survey billions of galaxies over a large portion of the sky, providing critical data to test cosmological models and theories. The Large Synoptic Survey Telescope, LSST, now known as the Vera C. Rubin Observatory, is another major upcoming project. Scheduled to begin full operations in the early 2020s, the Rubin Observatory will conduct a 10-year survey of the sky, capturing detailed images of billions of objects. Its wide field of view and deep imaging capabilities will allow it to study everything from asteroids in our solar system to distant galaxies and dark energy. Another exciting project is the Square Kilometre Array, SKA, a next-generation radio telescope that will be the largest and most sensitive of its kind. SKA will be built in 2 phases, with locations in South Africa and Australia. Once completed, it will have a total collecting area of over 1 square kilometre, allowing it to detect faint radio signals from the early universe. SKA will address a wide range of scientific questions, from the formation of the first stars and galaxies to the nature of dark matter and dark energy. Advancements in technology are also enhancing the capabilities of ground-based telescopes. The Extremely Large Telescope, ELT, currently under construction in Chile, will be the world's largest optical and infrared telescope. With a primary mirror measuring 39 meters in diameter, the ELT will provide unprecedented resolution and sensitivity. It will enable astronomers to study exoplanets, star formation, black holes, and the distant universe in greater detail than ever before. Adaptive optics is another technological innovation that has significantly improved the performance of ground-based telescopes. This technology corrects for the distortions caused by Earth's atmosphere, allowing telescopes to achieve near space-based quality images. Adaptive optics has been applied to many existing telescopes, enhancing their ability to observe faint and distant objects with greater clarity. The combination of these technological advances is transforming our ability to explore and understand the universe. Each new telescope and observatory provides new tools and perspectives, allowing scientists to probe deeper into the mysteries of the cosmos. These advancements not only expand our knowledge, but also inspire new questions and avenues of research. The ongoing development of space probes and missions continues to push the boundaries of our exploration. The New Horizons mission, which conducted a flyby of Pluto in 2015, provided the first close-up images of this distant world, revealing a surprisingly complex and dynamic landscape. New Horizons has since continued its journey into the Kuiper Belt, exploring other distant objects and shedding light on the outer regions of our solar system. The Parker Solar Probe, launched in 2018, is another groundbreaking mission. It is designed to study the Sun's outer atmosphere, or corona, by flying closer to the Sun than any previous spacecraft. Parker's observations are helping scientists understand the mechanisms that drive solar winds and space weather, which have significant impacts on Earth and our technological systems. The Mars rovers, including Curiosity and the more recent Perseverance, have transformed our understanding of the Red Planet. These rovers have explored the Martian surface, analyzing rocks and soil, and searching for signs of past life. The Perseverance rover, which landed in 2021, carries advanced instruments to study Mars's geology and climate and will collect samples for future return to Earth. These missions provide valuable insights into the history and potential habitability of Mars, paving the way for future human exploration. Looking to the future, planned missions such as the Europa Clipper and the Dragonfly mission to Titan aim to explore some of the most intriguing moons in our solar system. Europa Clipper, scheduled for launch in the 2020s, will study Jupiter's moon Europa, which is believed to have a subsurface ocean beneath its icy crust. The mission will investigate the moon's potential habitability and search for signs of life. Dragonfly, set to launch in 2027, will send a rotorcraft to Saturn's moon Titan, exploring its diverse and complex environment. Titan's thick atmosphere and surface lakes of liquid methane and ethane make it a fascinating target for studying prebiotic chemistry and the potential for life. The advancements in cosmology and space exploration are not just about collecting data and making discoveries. They also involve the development of new technologies and techniques that can have broader applications. For example, the technology used in adaptive optics for telescopes is also being applied in medical imaging, improving the clarity and precision of images used in diagnostics and treatment. The engineering and problem-solving required for space missions drive innovation in materials, science, robotics, and other fields, leading to benefits beyond astronomy. Hypothetical scenarios and speculations. The exploration of hypothetical scenarios and speculations in cosmology opens up some of the most intriguing and mind-bending questions about our place in the universe. These ideas push the boundaries of our understanding and challenge us to think beyond the known and the observable. Among these fascinating topics are the Fermi paradox, the simulation hypothesis, and the possibility of alternate dimensions. The Fermi paradox is named after physicist Enrico Fermi, who famously asked, "Where is everybody?" This paradox highlights the contradiction between the high probability of extraterrestrial life in the universe and the lack of evidence for or contact with such civilizations. Given the vast number of stars and planets in the Milky Way galaxy alone, it seems statistically likely that intelligent life should have arisen elsewhere. Yet, despite our efforts to detect signs of extraterrestrial life through programs like SETI, Search for Extraterrestrial Intelligence, we have found no definitive evidence. Several explanations have been proposed to resolve the Fermi paradox. One possibility is that intelligent civilizations are rare or short-lived. Life might frequently arise, but the development of advanced technological societies could be an infrequent event. Alternatively, civilizations might self-destruct before they can establish contact with others, through wars, environmental degradation, or other self-inflicted disasters. Another hypothesis suggests that advanced civilizations may choose to avoid contact with us. They could be observing us silently, either to allow us to develop independently or because they have ethical reasons for non-interference. This idea is sometimes referred to as the zoo hypothesis, where Earth is seen as a kind of cosmic zoo being observed by advanced extraterrestrial beings. It is also possible that we are not looking in the right way or at the right times. Advanced civilizations might use communication methods that we do not yet understand or are unable to detect with our current technology. They might also be located in regions of the galaxy that are difficult for us to observe. These possibilities highlight the limitations of our current search methods and the need for innovative approaches to finding extraterrestrial life. The simulation hypothesis presents another profound and speculative idea about our reality. Proposed by philosopher Nick Bostrom, this theory suggests that our universe might be an artificial simulation created by a highly advanced civilization. According to this hypothesis, it is possible that future civilizations with computational power far beyond our own could simulate entire universes, including conscious beings within them. If such simulations are possible and numerous, then it is statistically plausible that we might be living in one. The simulation hypothesis raises profound questions about the nature of reality and our place within it. If we are living in a simulation, then what we perceive as physical reality might be nothing more than a complex digital construct. This idea challenges our understanding of existence and the fundamental nature of the universe. It also leads to philosophical questions about the purpose and meaning of life within a simulated reality. One potential way to investigate the simulation hypothesis is to look for anomalies or inconsistencies in the laws of physics that might suggest an artificial origin. Some scientists have speculated that certain unexplained phenomena, such as the behavior of subatomic particles or the nature of dark matter, could be clues to the underlying structure of a simulated universe. However, proving or disproving the simulation hypothesis remains a significant challenge, as it requires a level of understanding and technology that is currently beyond our reach. The concept of alternate dimensions is another speculative area of cosmology that captures the imagination. The idea that there could be higher dimensions beyond the familiar three dimensions of space and one of time is a cornerstone of theories like string theory. In string theory, additional dimensions are compactified or curled up in such a way that they are not observable at everyday scales. These higher dimensions could have profound implications for our understanding of the universe. If higher dimensions exist, they could influence the behavior of fundamental forces and particles in ways that we do not yet fully understand. For example, gravity could be stronger or weaker in different dimensions, which might explain some of the anomalies we observe in the behavior of galaxies and cosmic structures. The existence of higher dimensions could also provide a framework for unifying the fundamental forces of nature, offering a more complete and coherent picture of the cosmos. The possibility of alternate dimensions also opens up fascinating speculative scenarios. Some theories suggest that there could be parallel universes or branes existing in higher dimensional space, each with its own unique properties and physical laws. These parallel universes might occasionally interact with our own, leading to observable effects such as unexplained cosmic events or anomalies in the behavior of particles. The exploration of alternate dimensions is not just a theoretical exercise, but also has practical implications for our understanding of the universe. Experiments at particle accelerators like the Large Hadron Collider, LHC, are probing the fundamental nature of matter and energy, searching for evidence of higher dimensions and other exotic phenomena. These experiments push the boundaries of our knowledge and could potentially reveal new insights into the fabric of reality. As we contemplate these hypothetical scenarios and speculations, we are reminded of the vastness and complexity of the universe. The Fermi paradox challenges us to consider the possibility of extraterrestrial life and the factors that might influence its detectability. The simulation hypothesis invites us to question the nature of reality and our place within it. The exploration of alternate dimensions expands our understanding of space and time, opening up new possibilities for understanding the cosmos. These speculative ideas highlight the importance of imagination and creativity in scientific inquiry. They push us to think beyond the boundaries of current knowledge and to explore new frontiers in our quest to understand the universe. While these ideas may seem far-fetched or speculative, they also represent the cutting edge of scientific thought, challenging us to expand our horizons and consider the deeper mysteries of existence. Each new discovery and each new theory brings us closer to understanding the profound questions that lie at the heart of cosmology. The exploration of these ideas not only expands our knowledge, but also inspires us to think deeply about the nature of reality and the fundamental principles that govern the cosmos. The quest for knowledge. So does beyond the observable universe even exist? To address the question of whether anything exists beyond the observable universe, we need to explore both the limits of our current scientific understanding and the philosophical implications of those limits. The observable universe is defined by the cosmic horizon, beyond which we cannot see due to the finite speed of light and the age of the universe. However, the very term observable universe implies that there could be more to the universe than what we can observe. From a scientific standpoint, the concept of the observable universe does not negate the existence of regions beyond it. The observable universe is a sphere with a radius of about 46.5 billion light-years, centered on the observer. This limit is set by the distance light has traveled since the Big Bang. However, the universe itself is believed to be much larger, possibly infinite. The theory of cosmic inflation, which posits that the universe underwent a rapid expansion shortly after the Big Bang, suggests that the observable universe is just a tiny fraction of the entire cosmos. Inflation theory explains the uniformity of the cosmic microwave background radiation and the distribution of galaxies by proposing that regions beyond our observable universe were once much closer together. During inflation, these regions expanded exponentially, becoming far beyond our current observational capabilities. If inflation is correct, then the universe is much larger than the observable part. There could be vast regions with galaxies, stars, and potentially even different physical laws, depending on the variations in the inflaton field that drove inflation. These regions are beyond our current reach, but they exist according to the same physical principles that govern our observable universe. The multiverse hypothesis, supported by various theories such as string theory and the many worlds interpretation of quantum mechanics, suggests the existence of multiple universes beyond our own. These universes could have different physical constants and laws, making them fundamentally different from what we experience. In some versions of the multiverse hypothesis, these universes are causally disconnected from ours, meaning we could never interact with or observe them directly. The existence of a universe beyond the observable raises profound philosophical questions about the nature of reality, knowledge, and existence. The concept of an unobservable universe highlights the limits of human knowledge and observation. While science relies on empirical evidence, the existence of regions beyond our observational capabilities challenges us to consider what we can know and how we can know it. The distinction between the observable and unobservable universe underscores the idea that there may always be aspects of reality beyond our comprehension, pushing us to continually refine our methods and theories. If regions beyond the observable universe exist, what does this mean for our understanding of reality? Philosophically, this suggests that reality is not confined to what we can perceive. Instead, it includes a vast and potentially infinite expanse that we can theorize about, but never fully grasp. This idea aligns with the notion that human perception and cognition are limited, and that the universe operates on scales and principles that transcend our immediate experience. Dark energy and dark matter play crucial roles in our understanding of the universe's structure and expansion. While dark matter interacts gravitationally, helping to form galaxies and clusters, dark energy is thought to drive the accelerated expansion of the universe. If the universe continues to expand indefinitely, regions that are currently observable will eventually become unobservable as they move beyond the cosmic horizon. This ongoing expansion suggests that the observable universe will shrink over time relative to the total size of the universe. As more regions slip beyond our observational reach, the idea that there are vast unobservable parts of the universe becomes even more compelling. Advances in technology and observational techniques may extend the boundaries of the observable universe. For instance, more powerful telescopes, both ground-based and space-based, could allow us to see further and with greater detail. However, there will always be a fundamental limit imposed by the speed of light and the age of the universe. Theoretical models in cosmology continue to evolve, incorporating new data and refining our understanding of the universe. These models suggest that the universe is far larger than what we can observe, reinforcing the idea that the observable universe is just a small part of a much grander whole. Models like the Lambda CDM, which include dark matter and dark energy, provide a framework for understanding the large-scale structure of the universe and its expansion, suggesting a vast and intricate cosmos beyond our observational limits. The question of whether something exists beyond the observable universe touches on the very nature of cosmology and our quest to understand the cosmos. Scientifically, there is strong evidence to suggest that the universe extends far beyond what we can observe. Theories like cosmic inflation and the multiverse hypothesis provide plausible explanations for the existence of regions beyond our observational capabilities. Philosophically, the idea of an unobservable universe challenges us to consider the limits of human knowledge and the nature of reality. It invites us to think deeply about what it means to exist in a universe that is far larger and more complex than what we can perceive. Ultimately, the exploration of what lies beyond the observable universe is a testament to human curiosity and the drive to understand our place in the cosmos. While we may never be able to observe or interact with these distant regions, the pursuit of knowledge about them continues to inspire scientific and philosophical inquiry, pushing the boundaries of our understanding and expanding our horizons. As we continue to develop new technologies and refine our theories, we may come closer to answering some of the profound questions about the universe's vastness and complexity. Until then, the mystery of what lies beyond the observable universe remains a powerful motivator for exploration and discovery, reminding us of the infinite possibilities that await in the cosmos. I hope you enjoyed this video. If you did, feel free to leave a like and subscribe to the channel. Thanks for watching.